focus of today's lesson is on radians and degree measures, and we start by talking about angles. So whenever we're talking about an angle is nothing more than two rays that are connected. And we like to talk about one of them being the terminal side and the initial side. So we start at the initial side. They both share the same vertex. We're going to the terminal side. That is an angle. Okay? So we have to make sure that we're understanding what terminal and initial side are. And this is going to be basically a quick vocabulary lesson. The next piece then says that angles are in standard position provided that the initial side is on the positive x-axis. So if the initial side is the positive x-axis, then the terminal side, we talk about its measure based on that. So this is our standard position. So when we have angles in standard position, if their measure is in a clockwise fashion, that's considered a negative angle. And if it's in a counterclockwise fashion, that's a positive angle. So here's our initial ray. If I'm going from that initial ray to this upper terminal ray, that is a positive angle. Always counterclockwise is always considered positive. From this initial ray to the terminal ray down here is considered a negative angle, counterclockwise, or plain old clockwise. So far, so good? All right. When we want to name coterminal angles, we want to know what are some other angles that have that same terminal ray. They all have the same initial ray if they're in standard position, but what are other angles that have the same terminal ray? So for example, this angle is a very large angle in a counterclockwise fashion. And this angle also has that same terminal ray in a counterclockwise fashion. So these two angles are equivalent, but one would have a positive measure and one would have a negative measure. They have the same terminal ray. So far, so good? Okay. And if I have an angle with an initial ray in standard position and a terminal ray, I can talk about that angle, or I can rename it as an angle that has done a full revolution plus that initial angle. So far, so good? We can add more than one revolution or more than one rotation around the origin. So, throughout geometry and algebra 2, we always talked about measures of angles in degrees. In algebra 2, we introduced another one as well, but in geometry, you weren't aware that there was anything other than degrees. 1 degree is 1/360th of a complete rotation about the vertex. So I made that 1 degree angle very, very large so you could see that it's not just a straight flat line. If I had only made this angle about this long, you would think it was just a plain old line. But 1 degree is a very tiny, small amount. It's 1/360th of a full revolution about the vertex. Okay? That's how we define it. So if I asked you to find two coterminal angles, one positive and one negative, for the given angles, what are we going to do? So, absolutely. Add 360 and subtract 360. So if it helps you to visualize it, if I put my axes here, a 30-degree angle is starting with its vertex at the origin, its initial ray at the positive x-axis, and we have gone 30 degrees, that's roughly 30 degrees, there's my terminal ray. This is a 30-degree angle. So if I add 360 to 30, we get 390. That is a coterminal angle, a full circle plus 30 degrees more gets me a coterminal, one that has the same terminal ray. And then if we take that 30 and we subtract 360, take away a revolution, we'll be in the same position, but it will have a negative value. So I'm starting at 30, and I'm going 360 degrees back. What does that measure? A negative 330 degrees, because counterclockwise is going to be positive and clockwise is always negative. So far so good? You guys remember this, right? Okay, just a refresher. So 135, if you don't want to visualize it, you simply want to use your shortcut, by all means do that. Anybody want to see 135? Okay, so what are we going to do to 135? Yep, add 360. Get 495. And 135 minus 360 will get us a negative angle. 225 degrees in the clockwise direction. Okay? Feeling good? All right, next example. Unit circle. You guys said, oh, gosh, I remember the unit circle. Some of you are groaning. And we're going to become really good friends with the unit circle and know it intimately. Okay? All the insides and outsides and all parts of it. So on our unit circle, I have given you little tick marks, basically, and those tick marks are every 15 degrees. So I've kind of shaded the ones that we're going to be using in a different color. So this might be where you would use some colored pencils to make all of your 30-degree angles one color, and all your 45-degree angles another, and all of your 60-degree angles another, if that helps you. Color's a good thing. But we want to know the special relationships or the special measures of the special angles, the 30s, the 45s, the 60s. So as I work our way around, 0 is the positive x-axis, and then we start working our way counterclockwise for a positive angle. So skip the very first tick, and the next one is going to be 30 degrees. These are all by 15s. 15 more than 30 is 45. 15 more than 45 is 60. You're going to skip the next one, which would be 75. It's not a special angle. And then to the top is 90 degrees. Then we skip the next one, which is another 15 degrees, so 105, and at 15 more is 120. So label 120. 15 more than that is 135. Then 150. We skip the 165, and we mark 180. Okay. Then we skip 15 more than that and go down to 210. Then 15 more is 225. 240. Skipping 1 to 70. And then we skip 1 and go to 300. 315. 330. And we skip the next one, and then we're at 360 again. Of course, we could continue to go around, but there's no real reason to. Good? Got them all? Why do we call it a unit circle? No idea? Anyone see what your radius is on your circle? How far out are we going? To the right, to the left, up and down? 1. So this is a unit circle because it has a radius of 1. All right, everybody ready? All right, here we go. So, radian measure. If we start with any old radius and we draw a circle with that radius of r, and then we take that radius and we measure it across the arc of that circle, one of those equivalent arcs with radius of r is going to be 1 radian, then 2, then 3. But we're a little bit short. How much short? 3.14. So there's 1 radian, pi radian. And then another half of a circle is another pi radian, for a total of 2 pi radians. Okay? Doesn't matter what size your radius is. It doesn't have to be like a unit circle with a radius of 1. Whatever that radius is, we make a circle. And if we take that radius and we mark off an arc of that radius, that's 1 radian. Okay? Arc and the radius are the same. The arc length and the radius are the same. There's 2 radians, 3 radians, a little bit more makes it 3.14159 radians. So 2 radians for the whole rotation. Make sense? 2 pi radians. All right, so here's a formula that will help you remember that. Theta, our angle, has to be in radians. Is equal to S, the arc length, divided by R, the radius of the circle. Okay? And we'll use that coming up. Theta equals S over R. But theta has to be in radians, not in degrees. Okay? So, here are some common radian measures. Okay, just like we like 30s and 45s and 60s, because those are from those special right triangles, the common radian measures are pi over 6, pi over 4, pi over 3, pi over 2, pi, and 2 pi. What does pi over 6 look like? A 30-degree angle. Okay? So anytime that you see some number of pi's over 6, you know that you're dealing with a 30-degree angle. Okay? What's pi over 4? 45-degree angle. So when you see a 4 in the denominator, you're dealing with a 45-degree angle. What about pi over 3? That's a 60-degree angle. Because when you see a 3 in the denominator, that means it's some form of a 60-degree angle in some quadrant. Pi over 2 is the same as 90 degrees. Half of pi, right? So that's pi over 2. 1 pi is equal to 180, and 2 pi is equal to 360. So the quicker you can make that connection in your head, that pi over 6 is 30, pi over 3 is 60, pi is 180, and so forth, the better off you'll be. Questions on this so far? Okay. So we want to find, just like we did before with angles and degree measure, some coterminal angles, but now they're in radians. So we have a 7 pi over 4 radian measure angle, and we want to know what's another coterminal angle with that. So what did we do when we were in degrees? Find other coterminal angles. Added and subtracted 360. So what do you think we're going to do if we want to find other coterminal angles with radians? 2 pi. Absolutely. We're going to add and subtract 2 pi. Okay? So now we get to work with fractions. Okay? So if we add and subtract 2 pi, 7 pi over 4, adding 2 pi, what do we have to do if we want to add those up? Good. We have to have a common denominator, so that's going to be 8 pi over 4. So 7 pi over 4 plus 8 pi over 4 is a total of 7 pi over 4 plus 8 pi over 4 is 15 pi over 4. And just leave it like that. No need to make it decimal, no need to convert it to a mixed number. Improper fraction is perfect. Okay, so that got us one positive angle. Let's find another coterminal angle. Let's take away 2 pi. So if we took 7 pi over 4 and we took away 8 pi over 4, what do we get? Negative pi over 4. So that's one positive, one negative coterminal angle. They'll end up in the same place with the same terminal ray. 5 pi over 6 plus 2 pi. What is 2 pi equivalent to? 360, but I'm sorry, as far as a fraction, 12 pi over 6, so 5 pi over 6 plus 12 pi over 6 gets us, and 5 pi over 6 minus 12 pi over 6 is, yep. We can handle that, right? No big issues there. Questions on this one? So back to our unit circle. We said that anything that had a 6 in the denominator is going to be a 30-degree angle. Because 30 degrees, and if we want to convert that to radians, what would we have to multiply it by? (180 degrees is the same as how many? 1 pi, right? Okay, so if I want to make my degrees go away, I would say 180 degrees and pi on top. They're equivalent. So the degrees cancel, the zeros cancel, and 3 over 18 is 6. So that's our pi over 6. So when you're counting, when you're labeling these, if you're going every 30 degrees, you're actually counting by pi over 6. This is 1 pi over 6. 30 degrees later is 2 pi over 6, which reduces to pi over 3. 30 degrees more is 3 pi over 6, which reduces to pi over 2. 30 degrees more, 4 pi over 6, which reduces to 2 pi over 3. 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 3 pi over 2, 10 pi over 6, so 5 pi over 3, 11 pi over 6, 12 pi over 6. So you can count every 30 degrees, you can count by pi over 6. When you're working with your 45s, that's a pi over 4. So you're counting by pi over 4. Every 45 degrees, you're another pi over 4 away. So 1 pi over 4, 2 pi over 4, pi over 2. 3 pi over 4, 4 pi over 4. 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4. So you'll get really quick at being able to label a unit circle. Or you can think of them as a part of a puzzle. This was a whole pi, there's half pi, and that's a fourth of a pi, and 3/4 of a pi, and so on. Okay. Questions on this one? All right, here we go. So, supplements and complements. We use this a lot in geometry. Someone remind me, what's the difference between complementary angles and supplementary angles? Or what are complementary angles? What are supplementary angles? Good. Complementary add to 90. So in radians, they're going to add to pi over 2. Supplementary add to 180. So in radians, they're going to add to pi. Okay? So we're going to ask you to find complements and supplements. So when we ask you to do that, we want you to, if it's in radians, we want you to give the answer in radians. If it's in degrees, we want you to keep it in degrees. And we know that you're more comfortable in degrees because you've had more exposure to it. So that's why we want you to keep it in radians if it's in radians. Okay? So, Dax, what are we going to do if we want to find the complement of 3 pi over 10? Not 360. Pi over complementary means they add to what, guys? 90 or pi over 2, right? So we need to take pi over 2 and take away the 3 pi over 10. Okay? So pi over 2 minus 3 pi over 10. What's our common denominator? So we've got 5 pi over 10 minus 3 pi over 10, 2 pi over 10, which reduces to pi over 5. And just leave it like that. No decimals, no nothing. Don't need to plug pi into your calculator. Leave it in that form. So that's the complement. Supplement. Excuse me. Thank you. We're going to take pi, which is the equivalent of 180, right? And we're going to take away that 3 pi over 10. 10 pi over 10, so yep, 7 pi over 10. Make sense? Come back and remind you, or you guys remember this stuff? Do we need to work with the 9 pi over 10 then, or keep going? Okay. All right, so that's it. We are working on section 4.1, page 269, 1 to 6 and 8 to 34 even.